Machine learning models require an obscene amount of data to be trained. But how is that data actually treated to make it learnable? To understand that, I'm creating two models from scratch. A support vector machine to make predictions on a CSV dataset, namely the experience level of an employee, and a multi-layer perceptron to distinguish pictures of cats versus dogs. They might sound completely different, but data processing is in principle quite similar. The support vector machine depends on Euclidean distance, Pythagoras theorem, so if we have a variable whose value is in the hundreds of thousands, this skews the learning in unwanted directions. To remedy this, we use normalization. We scale the large values down to match the other numeric features. The SVM dataset suffers from class imbalance. We want to distinguish 4 different experience levels, and over 60% of the examples in the dataset are of senior level employees. Of course, we're not throwing away perfectly fine examples, so we apply a scaling on the loss function to incentivize the model to classify correctly the minority class just as much as the majority one. This prevents the model from just guessing the most likely class output. Our fancy line with a margin also has a high cardinality problem. Rather than one-hot encoding everything, we replace these columns with compact engineered features using 2 custom transformers. One that uses keyword rules to group job titles into 10 families and assign a seniority score, and one that groups countries by their median training set salary and assigns each a tier between 0 and 4. For the SVM, 36 pipeline and model combinations were tested to evaluate different strategies. Balanced class weighing was the single most impactful choice across all configurations. The radial basis function kernel outperformed linear on every pipeline, confirming that the experience level boundaries are not linearly separable. For the multilayer perceptron, luckily the cats and dogs images dataset is perfectly balanced, with the exact same number of pictures for both classes. However, 4,000 images is actually very little data, so we need to find a way to make the model learn, even from a small amount of examples. What we do is data augmentation. A cat is still a cat if the image is flipped horizontally, slanted, or if the photo is brighter. So we can add some more images by applying these augmentations. Similarly to what was done for the large salary numbers, we normalize the pixel values using ImageNet statistics. Why ImageNet specifically? Well, because we're doing something that is kind of a hack, but it's also very effective. You see, a 224 by 224 pixel image flattened to a vector has over 150,000 features. With only 4,000 images, the model cannot simultaneously learn what features matter and how to classify them. The solution is transfer learning, which is why we use the ImageNet standard. We first put the pet image through a pre-trained backbone and then connect the output of that to our own small network. The result? 95.6% accuracy, which beats every other tested strategy by around 30 percentage points, even a more sophisticated convolutional neural network. The gap is explained by prior knowledge. The ResNet 18 backbone used is pre-trained on 1.2 million images, which reduces the task of our model to learning a simple classifier on top of already meaningful features produced by the backbone. In conclusion, machine learning is deeply dependent on the quality of the data.